I'm Yuxin from the National University of Singapore. Today I will be presenting on the probing magnetization switching using the nonlinear magnetoresistance and anomalous Nernst effect. As we know, the most spintronic devices functions by detecting the relative magnetization between the two magnetic layers, or by measuring the magnetization in relation to the current direction. The later one simplifies the sample structure as no reference magnetic layer is inlaid. In the longitudinal measurements, this includes some, the later one includes some magnetoresistance effects like the AMR and the SMR. However, these two kinds of MR provide a symmetric response to the magnetization direction, meaning that they cannot distinguish between the opposite directions of magnetization. And on the other hand, the USMR depends on both the current direction and the magnetization direction. In a system consisting of a heavy metal and an in-plane ferromagnet, the signals from USMR are proportional to the m dot j cross z. And when the current j is along the x direction, the signal responds linearly to the y component of the magnetization my. Another contribution to the longitudinal resistance comes from ANE. It generates a voltage that is perpendicular to both the heat flow and the magnetization direction. As a substrate, it dissipates heat much faster than the air. It creates a temperature gradient along the z-axis. And when the electric field and the measurement direction are both along x direction, the ANE will produce voltage that is proportional to x dot m cross delta t, which is also linearly related to my. As we can see, both the USMR and ANE signals are proportional to my, so their net contribution can serve as an effective tool to probing the spinning state of the ferromagnet with in-plane magnetization. And although the USMR and the ANE have been observed in various systems, most previous studies have relied on applying a large external magnetic field. However, the behavior of these effects in the low field range has remained unexplored. So in our study, we focus on their ability to probing the magnetization switching in the low field range. Our study is based on the covalent boron and the platinum bilayers. And instead of using the lock-in devices, we patent our samples into the Wheatstone bridge. The Wheatstone full bridge can help to cancel out the offside, the thermal drift, and the first order signals. It allows us to directly measure the second order USMR and ANE signals from the voltage output. And with this setup, we investigate the magnetization switching process in samples with different types of in-plane anisotropy. And by comparing their results, we will explore how the factors like the deposition bias field and the element shapes affect the anisotropy and the magnetization switching process. The first sample is patterned in an ellipsoidal shape and deposited with a magnetic field along the x-axis. The external, and the bias field induces an in-plane anisotropy along the x-axis. And we then apply a small sweeping magnetic field from -30 to 30 offset. And the external field is in-plane, and the phi here refers to the angle between the external field and the x direction. And so from the second harmonic signal shows odd dependence on the external field. However, no typical USMR or AAE loops were observed in this sample. And the figure in the lower left corner displays the voltage difference at the zero external field between the forward and the backward sweeping. And it also confirms the absence of the USMR or ANE loops in this sample. And then we performed the same measurements on sample 2, which had a similar structure to sample 1, except that the bias field is along y-axis. And in contrast to sample 1, the second order voltage of this sample clearly shows the hysteresis loops, except at the angle of 165 degrees. These results provide the key insight into the magnetic switching of the sample. And in the bottom figure, we observed two plateaus in the delta V here. And between the two plateaus, there are a narrow range where the delta V is near zero. And this plateau suggests that the presence of a finite distribution of the AtC-axis in a certain direction. And the third sample has the same structure with the first two, but no bias field was applied. Similar to sample 2, the results show clearly loops except at 165 degrees. However, the magnitude of the delta V is about half that of the sample 2. And to further investigate the effects of the shape anisotropy, we fabricate sample 4, which consists of 4 circular elements. And due to the small size of the sample 4, the hysteresis loops are significantly reduced, and the loop disappears at angles near 0 and 180 degrees. And to better understand these results, we conducted the simulation of the second order signals. In this structure, the second order voltage consists of 3 main components. The VFL represents the AMR and the SMR signals induced by the field-like effective field. And this VFL is proportional to the changing the magnetization direction delta beta here induced by the effective field. And based on our calculation, the sum of the field-like effective field and the Oxford field is much smaller than the anisotropy field HK. So it allows us to ignore the first term from the equation. This slide shows the simulation results, and we first assume that the magnetization is uniform around throughout the entire element. And here the angle gamma refers to the angle between the AtC-axis relatively to the x direction. The simulation results with gamma equals to 0 degrees closely match the experiment results from the sample 1. And when the gamma is 90 degrees, the simulations are similar to the experimental results for the sample 2, which is updated with a bias field along y direction. And a small difference is that in the simulation, the loop disappears at 180 degrees and 0 degrees, but in the experiment, it vanished at 165 degrees. This difference indicates that the effective AtC-axis of this sample of the sample 2 is offside by 15 degrees from the y-axis. And it's likely due to the shape anisotropy or the age effects. And for the sample deposited without any bias field, there's no well-defined easy axis across the entire element. However, the shape enthalpy and age effects prevents the sample from being completely anisotropic. To simulate this kind of sample, we assume that the sample consists of magnetic domains with easy axes aligned in two primary directions, the gamma 1 and gamma 2. Here the rightmost figure shows the results with gamma 1 equals 0 and gamma 2 equals to 75 degrees. And these results are,
Yeah.
I am almost finished. Okay. And these results align with the experimental results of sample 3. And here is the summary, and that's all for my presentation. Thank you.
Thank you, Yuxin. Very nice talk. Now the floor is open for the questions from the participants. Okay, if there is no question, I have one question. So
okay.
basically,
Sorry.
yeah. So so the what you said is the nonlinear signal obtained electrically. So which is corresponds to your transverse magnetization component. So how sensitive is this method for small variation of magnetization?
So can you repeat that? I can't hear very clearly.
Yeah. So for the nonlinear signal, so
Yeah.
you basically obtain electrically, right? To the transverse of magnetization components. So my question is, how sensitive it is for the small variation of magnetization?
Oh, the sensitivity, right? As oh, sorry, my computer sucks. As I showed in my results previously, our measurement is between the range of tens of Oersted. So this is I think the sensitivity of this probing the magnetization switching will down to the tens of Oersted range. Yeah. And for the smaller range, maybe in the future, we will explore more on the smaller range.
Okay. Yeah. So we can have one more questions. The participants, if there is any question, please yeah, raise your hand or just type in message. Okay. Yeah, if there is no more questions, thank you so much for your nice presentations. We'll